I would like to, it's my great honor to present the recent and some of our works on the coherent photon production, mainly on gypsum in Haiwan collisions. So my name is Wangmei from the University of Science and Technology of China. So since this is the this is the first talk in the section, so I would like to give a brief introduction to the photon production in Haiwan collisions. So in Haiwan collisions, for the colliding nuclei is moving with the speed close to the speed of light. So due to the Lorentz contraction, the electromagnetic field is very similar to that as real photons. So a formula first suggests to replace this electromagnetic field by the flux of crystal real photons. So this is how the photons coming from. So this due to the coherent limitation, so these photons are crystal real, and also here at least the form momentum of the crystal real photons. So you can view the photons also as partons being presented with the fast-moving ions. And because the electromagnetic field is long-range interaction force, so the extent of the photons swarming about the ions is very large, which means that when you have no nuclear overlap, when the colliding nuclei is just passing by, for example, the impact parameter is greater than the sum of the two colliding nuclei, you can still have interactions. So here I take an example of the photon production of rho at the Rick top energy in go-go collisions. So the average production radius is about 40 fermions, which is larger than the sum of the two colliding nuclei. So that means that collision happens in so-called ultra-peripheral collisions. There's no nuclear overlap. So with these crystal real photons, which makes that each Haiwan collider or also a photon collider. So with these crystal real photons, we can have photon-photon interactions. The photon emitted by one nuclei interact with the photons generated by the other nucleons, which can give us production of dileptons and also particle-antiparticle pairs. But this is not the topic we are focused on. We are focused on the photon-nuclear interactions. The immediate photon interact with the target nucleus, which give us the production of vector meson. For example, rho omega 5 gypsum, and gypsum is really what we focus on in this presentation. So we can have photon-photon interaction and also photon-nuclear interactions. And for the photon-nuclear interactions, it can be coherent or incoherent. Coherent means that it interacts with the whole nucleus, and the incoherent means it hit individual nucleons which break the nucleus. So conventionally, we only in the past we only believe that the coherent production only exists in ultra-peripheral collisions, which to keep the coherent requirements, because when you have nuclear overlap, the nuclei will be broken up, which we thought that it cannot keep coherent anymore. Okay, for the vector meson photon production, it can be viewed as its production can be viewed as this cartoon by the chargeless polymer exchange. So you can view the polymer as two gluons in the language of QCD, and also with the self-interactions between the two. It is viewed as a gluon ladder. So for the light meson production, it can be usually treated by the vector meson dominant model. For example, the rho omega 5. And for the heavy Quarkian production, because it is heavy, it can be treated by the PQCD. And in particular, it is sensitive to the Gluon distributions. So as shown in this formula, for the forward scattering cross-section, it is proportional to the Gluon density square, which means that it can directly determine the Gluon distribution. And as we know, for the Gluon distribution, it has large uncertainties. large uncertainty for large uncertainty because the gluon didn't carry electric charge. It cannot determine that it cannot determine directly by the DIS measurement. So here I show the two PDF set, one for EPPS 16 and also one for NC-TEC 15. So you can find that the NC-TEC 15 has a much narrower band, but it does not mean that the NC-TEC 15 is more advanced. It's only because for the EPPS 16, so they consider they have adopted more parametrization functions. So in the past version, the EPPS PDF set also has a narrow band, but we consider more parametrization for input. So they have large uncertainties. But for the both these two PDF sets, as we can find, that it has large uncertainties. So the measurement in of Quark from photon production can help us to constrain the NPDFs. So let's look at the measurement, existing measurement from mostly from the HC. So for the wrong one, it has at least measurement at the mid and forward rapidity, and also CMS measurement at the forward rapidity. For the wrong truth, it has the LCB measurement and also Alice measurement at the forward rapidity. So you can find that the measurement is comparing to the uncertainty band is rather precise, right? So it is powerful to constrain the NPDF. So how it can be how this measurement helping us to constrain the NPDF. So in the following in the next following slides, I will show you how this measurement can improve our understanding of the NPDF for lag at LC collision analysis. So the framework is so that it is kind of the impulse approximation. So for the cross section, for example, for the cross section, you have collisions. It can be described by this equation. So you have production from one direction, and also you have the production in another direction. And so this is the photon flux, and so this is a gamma A cross section. So the photon flux, it can be well described by the EPA approach. And for the cross section, it can be further read as these formulas. It can be read as the forward scalping cross section, and also with the form factor. So if we're using the Wood-Saxon distribution for the Wood-Saxon distribution for the nucleon, we can directly calculate this term, and we can extract the forward scattering cross section. And as we know, the forward scattering cross section is proportional to the Gluon density distribution square. And if we know the forward scattering cross section in gamma p, then we can direct extract the shading the shading of light. And for the gamma p cross section, we have worldwide measurements mainly from the hair and root measurement, and also have at least HCB measurement, and it can be parameterized using this formula, and you can find that this parameterization describes the worldwide measurement reasonably well. And if we know the slope of the distribution, so that we can get the forward scattering cross section, and if we make a ratio of the gamma A to gamma P, then we can extract the shading factor. But keeping in mind, but we have ambiguous in determining the x as you can find for the here. So for each direction, it has an x component. So for the production at each rapidity, it has two components: one high x contribution, one low x contribution. But so if we put impulse approximation and in the plot and comparing to the measurement, so you can find that the impulse approximation it is significantly larger than the measurement. So the gap between the two, the difference between the two, is the shadowing effect. And at the middle rapidity, so it's a special case because of the low x contribution and high x contribution. So the x is equivalent. So you can directly get the shadowing for middle rapidity. However, for forward rapidity, so it has high s and low s contribution. You need to convolute that out. But mainly the highest contribution is dominant. So you can if you look at the forward rapidity, so it mainly the dominant contribution is from the highest contribution. And from the left and the right plot, you can find that it has a significant shadowing effect. And if you're going toward forward rapidity, which means high x, the shadowing effect became less. So how can we put this measurement in the PDF set? So we can using a method so-called Bayesian reweighting. So for the Bayesian reweighting, if we taking the for example the EPBS16 or NCTEC15 as a baseline, so we can construct a PDF replica by its Hessian error set. And for each quantity, depending on the PDFs, it can be determined using this formula. And for new measurement, for new input, the reading PDF can be evaluated by these following equations. Here I didn't. So if you are interested in the details, you can look at the reference showing here. But in this presentation, I wouldn't go into details because of the time limit. So after putting all these precise measurement in the PDF set, we can get the reweighted result shown as the pink one, both for the EPBS16 and also for NCTEC15. So you can find that the UPC measurement dramatically reduce the uncertainty band, both for the EPBS16 and for the NCTEC15 case. So you can observe significant shading effect at low x for both PDF at small x. Okay, and as I just mentioned, for the measurement in hierarchical collisions, we have ambiguity of x determination, but this will not a problem in the future EIC complex, because for EIC it only has production from one direction, so the electron will the electron will emit the photon, and the photon will collide with the nucleon. So here is the projection from the with the ECDE detector set up. For the ECDE detector, it covered so it mainly covered the gypsy rapidity less than 3.5, and also for the collision energy select as 10 GeV electron hit on 100 GeV gold. So here I show also the EPBS16, and also the projection is just seated at the center, and also within almost negligible synthetic uncertainties. So which means that at the future EIC we have the opportunity to directly determine the shadowing from the measurement. And also, if you are interested, you can look at the presentations recently given at the workshop of physics opportunities with Havel Calcania at the EIC. Okay, so for the past few slides are showing the result from the UPC measurement. However, as we know, so with the efforts of experiments and also theoretically, we know that we also have production in non-UPC clearance, for example, for peripheral clearance. So the story starts from the Alice measurement in 2016. So Alice has made measurement for different PT range and also for different centralities. So you can find for the relatively large PT range, for example, PT larger than 0.3. So the RA for the nuclear modification factor at each centrality is less than 1. So which means we have suppression. So that is not writing, right? Because we have screening and also co-nuclear matter effect. But if you look at the red point for the PT less than 0.3, you can find huge enhancement at the peripheral clearance. Merely if you look at the most peripheral one, the enhanced factor can reach 7. So it cannot be explained by the hydronic production and also modified by the hot medium effect or co-nuclear matter effect. And we know the only gain effect for the hydronic for the overlapping region is the regeneration. However, we know that for that small PT range, PT less than 0.3, the effect should be negligible, and also we are guessing it's coming from coherent photon-nucleus interactions, and also later on. So at the start, we made almost the same measurement. We measured the production at the weak top energy for gold and uranium. For gold and uranium, you can find. For also, if you look at the nuclear modification factor as function of transfer momentum for different centrality beams, you can find that at the lowest PT range for peripheral clearance, so the enhancement factor can reach 30 to 40 for gold and uranium. So we also observe significant enhancement. But if we assuming the photon production is the source, then we should expect that the uranium should have the enhanced factor for uranium should be larger than that of gold. Indeed, for the central value, it's larger than that of gold. However, due to the limited statistical uncertainties, and also if we combine the statistical and the thematic uncertainties, we cannot say that because we cannot tell the difference as within uncertainties. And furthermore, we have also made a measurement of the T distributions, because the T distribution is more related to the production site. So you can relate it to the transverse spatial distribution of Gluon. So if you assuming that the Gluon spatial distribution is the same as the nuclear distribution, so you can directly extract the slope parameter. So you can make comparison to that of assuming Wood-Saxon distributions. So the slope extracted from the T distributions is about 177. So this is very similar to the starlight prediction in UPC case. So which means that the target size should be the target size is the size of that gold. And also, furthermore, if you look at the fourth data point, the fourth data point is significantly lower than the exponential extrapolations. So this shows the hint of the interference. So unique phenomena only in coherent photon production you have collisions. So if you're comparing the shape in gold, comparing that to the calculations with interference, so show as the blue line. So you can find describe the data reasonably well. So from these two measurements from Alice and also from Star, we and also comparing to the theoretical calculations, so I think we can say that we observe the coherent photon production of gypsum in hadronic heavy clearance. And in the later talk, so Julia will talk about the measurement in HCP, the recent new measurement in HCP. So I will not cover it here. I will mainly focusing on the Star measurement and also the Alice measurement and comparing to the theoretical and even So we have additional source for the chip side from photon production. So the next thinking is that can this additional source present as a prop for the QGP? So we know for the QGP we have all the media effect, the color screening, the regeneration. So for the photon production of chip side, so it should have you should have no regeneration effect. And also for the co-nuclear matter effect, it should also be modified by the PDF, but it should not have something like, for example, the initial state and energy loss. So does it mean that the original source can serve as a cleaner prop, for example, for the color screening? But first, we should know the baseline. For example, for the IA measurement for the chip side for hadronic contribution, we just using the PP measurement as a baseline. However, for the photon production, we cannot using that as a baseline. We need using the forward scattering cross section, for example, for gamma p as a baseline, and also do some extrapolations. Still, so we can using the framework the impact observation described in the previous slide. So if we comparing the impact observation show as the blue line and comparing to the data, so this plot is for the measurement at the read, and so this is comparable with that at least in that clearance. So you can find for the measurement at the rig, you can find if we assume everything is if we assume everything there's no shading, everything is just exactly the same as that happened in gamma p. So you can find that is all estimated data. All estimated if you considering the whole sensitivity range. And also the conclusion is the same. Also, I think for the Alice measurement, so it's obvious that if for the impact observation, it is all estimated data. And then if we put in the shading effect, observe extract from the UPC measurement just from the previous slide, so we'll get the black curve, the solid black curve. So if you're comparing to the measurement, you can find both for RIC and also HC, it can describe the preferred data reasonably well. So this is also not surprising, because if you consider shadowing, it means that you're assuming that everything happens in peripheral clearance is exactly the same as that in ultra peripheral clearance. And because of a peripheral clearance, the situation is very close to the case in ultra peripheral clearance. So it should reproduce the measurement. And we further considering the case of the observation effect. So what is observation effect? But it means that because in the overlap region, showing as this cartoon in the overlap region, so you will have strong interactions. We have strong interaction which may identify the photon production, which leads to decoherent, which means that it cannot be coherent anymore. So we can exclude that the overlap region out, and also you can say that because the media they will evolve, they will become larger, so it may swallow a larger area. But here in the calculator for the simplest case, we just exclude the nuclear overlap region out. So this is so-called observation effect, shown as the red one. So you can find that describe the data reasonably well. So it prefer to show that we have the hint of disruption from the medium. So we have the observation effect. If there's any, for example, the screening effect, it should be in addition to the red line. Okay, so and also recently we have Alice has also made a measurement from the round 2 at 5.02 TeV. So this is the result for at the middle rapidity. This is result at forward rapidity. And also, I think the conclusion is the same as what we showed in previous slides, in the last slide. Also, we can conclude that we have observed the hint of disruption from the medium, but we still need more statistics, more precise measurement at both, I think, at both mid and the forward rapidity, and also we would like to see the result towards central collision, because you can find that for different assumptions, so they have huge difference towards central collisions. Okay, so another so in the previous several previous slides are showing the recent experimental measurement in hadronic collisions. And also another very important feature of coherent production is the linear power. So it is linear polarized. So if you're looking at because due to the extreme Lorentz contraction, so the electromagnetic field is the electric vector is perpendicular to that of magnetic vector, and also perpendicular to the moving direction. And for the polarization, we know that for the photon, its polarization vector, it follows the electric vector of photons. So if you sit here, for example, so you will find that the photons is aligned along the radial direction. So it's well defined in position and momentum agent states, and also align the radial with the emitting source. So the linear polarized photons, so it has been observed in experiment and confirmed by a star collaboration, and according to the Jianzhou's theoretical calculation, that for gamma collision to dielectron, because the fully linear polarized photons, it will lead to cosine 4-5 modulation. So star has recently observed this cosine 4-5 modulation, and it has been published recently in PRL. So, and if we, sorry. Okay, should I go ahead? Okay, so because the photon is polarized, so it also, for the photon production, you also should have effect. For the photon production, because the production side is on the nucleus. So if you look at in this cartoon, so for the photon production, the polarization vector of the photon should be aligned along the impact parameter. And if we assume the holistic conservation, which means that the produced vector of meson inherits the photon state, so it will leading to the asymmetry distribution in angular distribution showing here. So the theta is phi. So with respect to the capital phi is represented the polarization vector. And we know that due to the indifferent effect, the vector method production in coherent photon production in hadron collisions, so they have the interference fringe. So it has orientation. It has a prefer in the angular, so in the momentum distribution. So it will lead to cosine 2 theta phi modulation, shown as this plot. And also, so in another star, for the star preliminary results, we observed this cosine 2 phi modulation, showing in this plot as the red data point. And then you can find for the theoretical calculations, it can constantly describe the data. And for the second, and so as I emphasized here, so the two sorts of interference pattern will resulting. It is resulting from the quantum spin momentum correlation, which will give us the cosine 2 phi modulation. And also we have also made the prediction, and you can find that it can describe the data reasonably well. So and also you can find that the second peak shows strong dependent on the detailed nuclear geometry, which means that we can using that to determine the nuclear for example, the Gluon distribution in the nucleus. However, so as I said, the polarization vector is is aligned along the impact parameter. So can we using that to direct the reaction plane? So, okay. So but if you're looking at the photon production looking at the photon production for rho and phi, so you can find that even in peripheral clearance at rig, the photon production is not dominant at very very low T. So which means that in the dirty probe you need to to considering the hadronic contribution. But for gypsy we didn't have and also for phi, even for phi, we didn't have, there's no experimental measurement yet because if you're looking at the acceptance as function of PT, you can find that you have negative contribution due to the acceptance. So, but this is not a problem for gypsy. So for gypsy, we can have because as I showed, both at Rick and Alice, we have huge enhancement, which means that the hadronic contribution should be really negligible. So it can helping us to determine the reaction plane within the gypsy. So this shows the polarization, the degree of polarization for the gypsy show as the red one. So the number of the P gamma it represents the alignment to the reaction plane. So the maximum value is 1, so you can find it has very good it has very good resolution at peripheral clearance. And also for this determination of reaction plane, it has no event by event fluctuation, because in the Goldwalker paradigm for the coherent production, so it is the average is averaging over the nuclear density distribution, and for the incoherent contribution, it reflects the fluctuation. So it could directly link the final flow to the initial geometry. So as a summary, so I show you that the vector method photon production in ultra peripheral clearance is having us to consider the MPDF, and also for the access of gypsy at a very low PT in peripheral clearance. So it can make a normal probe for the QAPT, and also may having us to determine the initial geometry. But first we need to confirm that there's this cosine 2 phi for gypsy, even in UPC and also in non-UPC in hadronic clearance, and then we can utilize that to determine the initial geometry. Thank you. That's all for my presentation.